There are many similarities between visual analytics and interactive optimization. The design of visual interfaces for optimization systems is an application of visual analytics. However, many optimization systems are automated. If you are thinking of building an interactive optimization system, come to our talk. We have prepared some tips for you.
Data stakeholders are rarely the data experts. Making tools for them means considering how they communicate about data. Rules are a convenient way for humans to express patterns in data, like we need high variable x and low variable y. In our human-in-the-loop approach, the user selects points of interest and can immediately see rules that differentiate those data from the rest. Lots more detail in the paper, even though it's short.
Hey everyone, I'm Jian-Guang, a PhD candidate at Purdue University, computer graphics major, and a research internship at Bosch Research North America. Here, we are presenting our recent research, Persevere, using factorized prototypes to visually interpret and diagnose deep neural network. This work is co-authored by research scientists at Bosch, Zhang Dai, Dr. Panpan Xu, and Dr. Liu Ren.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Blockchain has gained more attention and its applications are emerging. We collect 76 blockchain visualization tools and systematically classify them into 5 aspects: target blockchain, blockchain data, target audience, task domain, and visualization type. In the end, we look at open challenge in blockchain visualization.
Firstly, we extract contours of virions and distribution of spike proteins. From a newly estimated contour, a 3D mesh with evaluated triangles is obtained. In the last step, rules describing relations between protein instances are defined by the user. The resulting model is created by application of all rules on the generated 3D mesh.
Nowadays, data is often distributed and owned by different participants. There is an emerging need to provide a joint visualization, such as a TS&E projection, to serve as the full picture in data analysis. If the participants are privacy sensitive, how can we build a joint projection without data leakage? Conventional embedding algorithms, such as the TS&E, are designed for single-site computation and require data centralization. Privacy leakage may happen in 3 stages in the visualization pipeline.
Many techniques can be used to render and visually explore large 3D line sets with transparency. However, all these techniques differ in several aspects such as runtime performance, memory consumption, and image quality. In this work, we provide an extensive comparison study to discuss the advantages and drawbacks of transparency rendering techniques for large line datasets.
We present an efficient approach for volume and isosurface ray tracing of structured AMR data on GPU-equipped workstations, using a combination of 2 different data structures. Together, these data structures allow a ray tracing-based renderer to quickly determine which segments along the ray need to be integrated and at what frequency, while also providing quick access to all data values required for a smooth sample reconstruction kernel.
Exploring the emotions of students in classroom videos can help both teachers and parents know about students' learning status and further help teachers improve teaching. However, it is a non-trivial task to analyze the emotion evolution of a group of people from classroom videos due to 3 major challenges. We propose a visualization system which integrates the model uncertainty and supports both collective and individual emotion analysis.
TaxIMIS is an interactive visual analytics system to help tax officers identify suspicious tax evasion groups. The system integrates the traditional data mining algorithm and visual analytics techniques. 4 coordinate views are provided to support interactive exploration of tax evasion evidence. We demonstrate its usefulness through case studies using real-world tax data and expert interviews.
VIS has been successfully helping not only experts but also people who want to learn about AI. At VAS 2018, we presented GANLab, an interactive tool for learning about a deep learning model called GAN. But how does VIS help these learners? We conducted 2 evaluation studies, including log analysis of our demo used by over 100,000 people. We will be sharing our findings with you.
Tableau helps you see the stories in your data. It's designed to help you be smarter.
Hello, everyone. My name is Kanit Wongsuphasawat, or Ham. I'm from Apple, and I'll be the session chair for this Automate and Recommend session. We have 6 exciting papers for how we can automate the authoring of infographics, data story, mobile visualization, color palettes, and animation, as well as how to recommend contents from a visualization repository. So let's begin with the first paper, which is Retrieve, then Adapt, example-based automatic generation for proportion-related infographics. Chunyao from Peking University will be the presenter.
This is the presentation for the paper, Retrieve then Adapt, example-based automatic generation for proportion-related infographics, authored by Chunyao, Shizhao, Weiwei, Jian-Guang, Haidong Zhang, and Dongmei Zhang from Microsoft Research Asia. My name is Chunyao from Peking University, and I will be presenting the paper on behalf of my co-authors. Here is the agenda for my presentation. First of all, let me give you a little bit of background information about infographics. As a data visualization technique, infographics combine graphic and textual descriptions in an attractive manner. However, creating infographics is not an easy task, which requires professional skills and tremendous time, even for experienced designers, not to mention novice users with limited design expertise. That is why automating the design of infographics has attracted great attention in recent years. Using predefined blueprints is an easy approach to enable automated infographic design, which has been widely used in commercial softwares such as Microsoft PowerPoint and Adobe Illustrator. However, such blueprint-based approach has some limitations as well. First, as the number of blueprints is limited, such approach may easily generate homogeneous infographics and a lack of diversity. Moreover, it is difficult to enrich the blueprint library with low efforts, as designing blueprints is both complicated and laborious. By contrast, well-designed infographics are everywhere. When you search infographics on the internet, you can get a huge number of well-designed infographics. Compared to predefined blueprints, online examples are inherently rich in diversity and quantity. More importantly, design choices in these examples are generally appropriate and viable in practice, as they are made and endorsed by professionals. Based on the above observations, a natural question arises. Why not generate infographics by automatically imitating online examples? Here are some preliminaries of our research. First of all, considering various types of infographics, it is impossible to cover every category in one work. As a first step, we focus on the proportion-related infographics, which are most frequently used and whose design space is well studied in the previous research, text-to-VIS. As you can see, our framework takes a natural language statement as input, like it is estimated that more than 74% of users are female. We believe it is the most friendly way for people to use, especially for casual users. Then, the input utterance will be transformed into a set of visual elements. Such transformation is studied and realized in text-to-VIS, so we just follow the same input processing pipeline of text-to-VIS to collect candidates of visual elements. The core interest of our work is to study how to convert the visual elements into a new infographic by imitating online examples. To understand what visual elements are often used in infographics, we rank and select the top 10 frequently used ones in examples. Generally, they can be divided into text and graphic class. In text class, the top 5 frequently used elements are before, modifier, number, after, and the whole statement. In graphic class, they are single icon, donut, pie, bar, and pictograph, which is the combination of single icons. However, there are two critical challenges when developing such an example-based approach for proportion-related infographics. First, in a large collection of examples, how to find appropriate ones whose designs can be transferred to a specific piece of information. Second, even we find such a matching example, it is unlikely that the information is a perfect fit in terms of every design aspect. For instance, the text length in the user information may be different with that in the example. To address these challenges, we propose a two-stage approach called Retrieve then Adapt to automatically convert a piece of information to its infographic equivalents. In the retrieval stage, we build a retrieval system to help find appropriate example. First, intuitively, if the input can be represented by an icon and a text statement, examples that exactly have one icon and one text box are more likely to be candidates for reuse. Moreover, if the text of the input has a similar length to that in an example, the design of this example will be ideal for reuse. This motivates us to index examples by visual element types and their built-in attributes. Specifically, we manually annotate the built-in attributes of the collected infographics, including the number of characters for textual elements and the aspect ratio for graphical elements. As example index is composed of visual element types and built-in attributes, we need to transform the user input to concrete queries of the same form. On one hand, there are usually many valid ways to represent the same piece of information using infographics. On the other hand, the example library indicates the likelihood of different representations adopted in practice. Therefore, we propose to first learn a distribution about visual elements from the example library, and then generate user queries by sampling from the distribution. For example, given a user information, we have opportunity to sample query 1 with 0.35. And we also have opportunity to sample query 2 with 0.02. The last step is to retrieve the most similar example. Concretely, for a given example index and user query, we first match their elements by type. Then we calculate the distance between them by considering whether they have similar visual element types and built-in attributes. After obtaining the example, we start to initialize the draft. We first directly fit the new elements into the retrieved example. To avoid some distortion of graphic elements, we rescale the aspect ratio of them according to the long side. To maintain the text information complete, we recalculate the font size. In the previous stage, we generate an initial draft by reusing the design of the retrieved example. While the initial draft roughly conforms to design principles, spatial relationships between visual elements are not good enough in many cases. This is mainly caused by that built-in attributes in the query are often slightly different from that in the retrieved example. As is shown in this figure, the font size is too small and impacts the readability. Moreover, there is an excessive white space to the right side of the bottle icon. Therefore, to ensure the quality of generated infographics, we introduce an adaptation stage. In the adaptation stage, we use an MCMC-like solution to optimize the initial draft. We first set a start point. As the previous stage has generated an initial draft roughly conforming to design principles, we take the initial draft as a start point instead of randomly sampling one. We then propose a candidate design by randomly choosing an element and making proposal moves such as move the position of the selected element or change its size. We finally compare the candidate and the current designs. If it is better than the original design, we accept the proposed one. Otherwise, we just reject the proposed design with certain probability. To effectively discriminate which candidate design is better, we need to train a neural evaluator. However, we face two challenges. First, we should construct a training set with effective labels from the example library. The challenge is that the example library only contains labels for visual elements and attributes, while our task requires labels reflecting the quality of spatial relationships in a design. Second, we should learn a good feature representation for spatial relationships in infographics. To address the first challenge, we construct a training dataset. Specifically, we make random perturbations on collected examples. We assume that the larger the perturbation is, the worse the spatial relationships are. Thus, the original infographics and the corresponding less disturbed ones are good examples, while infographics with relatively larger disturbance are regarded as negative ones. As for the second challenge, we propose a recursive neural networks-based evaluation model to learn good features and discriminate which design is better. This figure shows the model architecture. First, as infographics are inherently hierarchical, we introduce a tributor to transform the infographic into a hierarchical tree in a top-down fashion. Then, the feature extractor, which is a recursive neural network, is used to encode the infographic into hidden vectors according to the hierarchical tree in a bottom-up manner. Finally, we build a scorer upon these hidden vectors to compute scores for spatial relationships in the infographic. In conclusion, we propose Retrieve then Adapt, an automatic framework for creating infographics by imitating online examples. The reasons we believe it is important are: our research opens up a new paradigm for automatically generating infographics, that is, example-based approach. For casual users, Retrieve then Adapt can generate infographics for direct use. For professional designers, it can provide design drafts to foster inspirations. That's all. Thank you.
Cool. Thanks for the presentation, Chunyao. We have a question from Wolfgang Eigner. So the question is, do I understand correctly that a single statement is transformed into a single visualization? Can several statements also be combined?
Sorry, are you asking me questions?
Yeah, so the question is from Wolfgang. The question is, do I understand correctly that a single statement is transformed into a single visualization? Can several statements also be combined?
As in our work, we can only handle the single step.
Thank you. So I think given the time and the schedule, I think we'll go to the next paper. But if you have more questions, feel free to ask more on Discord, and the authors will be answering in the channel. So the next presentation will be Calliope, a system for automated visual data story generation from a spreadsheet. And the presenter will be Danqing Shi from Tong University.
Danqing Shi, PhD student from Tong University. I'll be presenting our work, Calliope, Automatic Visual Data Story Generation from a Spreadsheet. This work is from the Intelligent Big Data Visualization Lab in Tong University. A visual data story is a series of meaningfully connected story pieces, known as data facts, represented in the form of narrative visualization. Such form is frequently used in a data-driven storytelling process due to its efficiency, in terms of supporting the comprehension and memorization of the data content. Although useful, creating a visual data story is not an easy task. To generate a visual data story, we need to learn a lot of techniques, such as data analysis, visualization, and scripting. To lower the technique barrier, we introduce an intelligent system, Calliope, to generate visual data stories directly from the import spreadsheet in a fully automatic process. Over the last few months, we have upgraded Calliope from the research prototype to the online platform. Users can upload, generate, and share their data story on this website. Before designing the system, we clear the definition of the data story. According to the reference, data story is a set of story pieces that are meaningfully connected to support the author's communication goal. Formally, a data story consists of a sequence of data facts that are connected by coherent relations. Here, we borrowed the definition of 10 fact types and 6 coherence relations introduced in the references. Furthermore, it is necessary to understand how a data story is created by a human designer. To this end, as data video is a frequently used narrative visualization form, we collected a set of data videos from YouTube and Vimeo by searching keywords, such as animated infographic, data video, and motion infographic. A total of 230 high-quality videos were selected and manually labeled for analysis. As a result, a set of statistics are able to help us answer a number of questions that are critical to the design of an automatic story generation system. For example, it suggests the frequently used fact types and coherence relations regarding our data video corpus. The study results also suggest the preferenced visualization charts given a fact type, and the narrative logic probably used following each fact type. Calliope system consists of two major components, the story generation engine and the story editor. The story generation engine is designed based on a logic-oriented Monte Carlo tree search process, in which a story is gradually generated data fact by data fact while searching through the data space. The generated story is visualized in the story editor as a series of captured visualization charts, whose data content, captions, chat types, and logic orders can be revised according to users' preferences. In our definition, Data facts are the elementary building blocks of a data story. We first gave a formal definition of data facts by simplifying the concept introduced in previous works. Formally, a data fact is defined by a 5-tuple: type, subspace, breakdown, measure, and focus. Type indicates the type of information described by the fact, including value, difference, proportion, trend, categorization, distribution, rank, association, extreme, and outlier. Subspace describes the data scope of the fact, which is defined by a set of data fields in the following form, where Fi and Vi respectively indicate a data field and its corresponding value selected to filter the data. By default, the subspace is the entire dataset. Breakdown is a set of temporal or categorical data fields based on which the data items are further divided into groups. Measure is a numerical data field based on which we can retrieve a data value or calculate a derived value by aggregating the subspace or each data group. Focus indicates a set of specific data items that require attention. To understand the above concepts, let's consider the following example. Given a dataset about the COVID-19 virus outbreak in China, the data fact describes the distribution of the total number of infections over all provinces when the country is China, and Hubei needs to pay attention. As summarized in the table, we add constraints on each fact field to ensure a clear semantics. Thus, each fact can be described by a syntax which is used for generating a textual description of the fact. We estimate the importance of a data fact based on its self-information weighted by its pattern significance. In particular, SFI estimates the significance of the data patterns described by the fact, which is calculated based on auto-insights techniques. And self-information IFI is defined based on the information theory and can be measured in byte using the following formula, where PFI indicates the occurrence probability of the fact given the input data. PFI is formally determined by the occurrence probability of the fact subspace and the probability of selecting Xi as the focus and choosing Mi and Bi to measure and break down the subspace given a fact type. The story design space could be extremely large due to the large number of possible combinations of fact fields, even based on a small dataset. The algorithm cannot generate all facts first and then pick up those important ones to build the story, as users cannot afford a long waiting time. We address this issue by introducing an efficient logic-oriented searching algorithm based on the Monte Carlo tree search. The algorithm generates a story by iteratively searching more informative and significant data facts to elaborate the story via 4 major steps: selection, expansion, simulation, and backpropagation. In this algorithm, we need to solve 2 critical problems. First, how to expand data facts in a narratively logical order during expansion. Second, how to estimate the quality of the generated data story during simulation. For the first problem, we investigated how coherence relations was used in data stories during our preliminary survey. Each new fact is generated by the rules according to the relation. For example, regarding to elaboration, we create a new fact by shrinking the scope of previous subspace via adding more constraints or setting a focus to zoom into a more specific scope. For the second problem, we propose a reward function that estimates the quality of each generated story via 3 criteria: diversity, logicality, and integrity based on the story's information entropy. Addresses the story's information entropy that indicates the expected self-information of the data facts in the story, which is used as the basis of the reward. Diversity estimates the variance of the fact types, which fact type will make the story vivid and attractive. Logicality estimates the logical coherence of a story. The higher logicality score indicates the story is more coherent and easy to follow. Integrity is the data coverage rate. A larger integrity indicates the story more comprehensively represents the input data. Gamma are the weighting parameters given by the users to balance the different criteria. When reward is maximized, the first part encouraged a more vivid, coherent, and comprehensive data story, and the second part ensures that the facts in the final story should be informative and significant. Now, let's look at the story editor. The story editor consists of three major views: the storyline view, the fact view, and the story visualization view. The user can upload data into the system, set the story generation goal, and adjust the parameters through the configuration panels. After clicking the generation button, the story generation engine is turned on, and the intermediate results are updated in real time on the user interface. The final generation result is a data story consisting of a series of data facts that are illustrated by a sequence of captioned visualization charts shown in the storyline view. In this view, we can interactively add or remove a chart, change its logic order, or edit on its caption. We can also revise the data content and visualization methods of each data fact in the fact view when necessary. Three visualization modes are provided in Calliope to help represent the generated story in different devices. The storyline mode fits well to the screen of a tablet or a laptop. The swiper mode facilitates the story exploration on a smartphone. The fact sheet mode shows the story as a poster that can be easily printed out. A user can also share the generated story with their friends via a link by clicking the share button. We evaluate Calliope system via three examples: two controlled user studies and a series of expert interviews. We demonstrate three visual data stories generated by Calliope, respectively based on three real-world datasets. The first example shows a story generated based on a COVID-19 dataset. The data record the numbers of daily infections, deaths, and hearings of COVID-19 in China from March 1st to March 21st. The generated story illustrates the daily mortality in China decreased in March, and the largest number was 42 occurred in March 2nd. Hubei was the most affected province. The total deaths in Hubei accounted for 97.4% of that in China, which was 423. A large number of patients recovered in March, showing the improving situation in China. Another story presents a dataset about startup failures. The data record a set of companies closed in China from 2010 to 2019. The story shows that numerous companies are closed in recent years, and most of them were located in eastern China. The most dangerous fields were e-commerce, social media, and local business. Most companies closed in these fields were still in the early stage before the Series A+ round, and some even closed without receiving any investment. Regarding the reasons, no business model and no market need were the most frequently occurring problems in these startup companies. In the first controlled user study, we estimated whether the logic generated by Calliope helps with the understanding of a data story. To this end, we compared our generation results with the fact sheets generated by DataShot, in which a set of selected data facts was randomly organized. Each participant was presented with two fact sheets of different topics from our data, one by Calliope and one by DataShot. They were asked to read the fact sheets carefully and compare two fact sheets from 5 specific aspects. The qualitative results show that, in terms of logicality and memorability, Calliope received more positive feedback than DataShot. And regarding comprehension, engagement, and dissemination, Calliope performs comparably to DataShot. The second experiment was designed to evaluate the quality of the generated logic. To this end, we estimated the consistency of the logic orders respectively given by users and generated by Calliope based on the same set of data facts. 20 participants were recruited. We first shuffled order of a set of data facts in a visual data story generated by Calliope, and then asked a group of users to restore the logic order by reading the chart and the descriptions of each fact. The result shows that the logic orders generated by Calliope were consistent with those generated by our participants. To further evaluate the usability of Calliope system, a series of interviews with 3 groups of expert users were performed, including 4 data journalists, 3 data analysts, and 3 senior visualization researchers. According to the questionnaire results, Calliope was rated relatively high in terms of the generated story, visualization, and system. A large number of positive comments were recorded during the interview. To conclude, we present Calliope, a novel system designed for automatically generating visual data stories from a spreadsheet. We introduce a novel story generation algorithm and a method to estimate the information quantity of a data story. The evaluation shows the power of our system. Calliope, powering the future with data narratives. With Calliope, a good story is just a click away from us. Welcome to have a try by yourself on datacalliope.com. If you have any question or meet any problem, welcome to contact us via calliope@idvxlab.com.
Cool. Thanks, Danqing, for the talk. And we have several questions on Discord. The top voted one is a question from Shirley. And the question is, do you consider the narrative structure in the data story?
Okay, thanks for everyone to hear my presentation. This question is about the usage of the narrative structure in the generation process. In our current research, we still focus on the semantic relation between two story pieces. According to our tree search algorithm, the generated story will begin in a general data fact as the root and then drill into the specific and informative part of the data. It can follow the general to specific pattern to tell the story. I think a promising future work is to consider other structure like parallel structure, which has proved that can help the memorability of the visual story.
Thank you. And there's another question from Jesse. That is it possible that the generated result may mislead the users?
Thanks for the question. I think the story generated by the Calliope system is based on the data facts in the spreadsheet. Thus, it always reveals the truth in the data. The possible limitation is the generated story cannot cover the whole spreadsheet and only cover a specific part of the data. However, our algorithm will try the best to provide the most informative facts to the users. And furthermore, users can continue to explore using our Calliope editor to refine the results. Yeah.
Cool, thank you for the answer. The next paper is MobileVisFixer, tailoring web visualization for mobile phone, leveraging an explainable reinforcement learning framework. The presenter will be Aoyu Wu from the Hong Kong University of Science and Technology.
Hello, I'm glad to talk about our studies about mobile-friendly web visualizations and present our method for automatic responsive visualization design. I'm Aoyu Wu, a PhD student from Hong Kong University of Science and Technology. I collaborated this work with Tong, Tim Dwyer, Bongshin, Petra, Isenberg, and my supervisor Huamin. Data visualizations are becoming more and more popular online, for example in social media and news articles. They are a powerful tool to tell stories and convey insights. However, this means that people are now frequently looking at data visualizations on much smaller screens than they were designed for. In particular, they may require significant adaptation to fit into mobile phone screens. For instance, in this chart, the legend becomes out of the view box on mobile screens, making the chart difficult to understand or forcing users to scroll the screen horizontally. Or the font size might be too small to read. For instance, the axis labels in this chart are too tiny. The text labels can be overlapping with each other as well, impacting the readability. In addition, the chart could have an aspect ratio which is quite different from the original version, potentially leading to some perceptual bias. Finally, white spaces used to aesthetically place a chart can become wasted places on mobile screen, which could be used more effectively. Those 5 mobile-friendly issues were identified in our survey of 374 visualizations obtained from different web sources. Unfortunately, they appear to be quite common. The majority of them suffer at least one mobile-friendly issue, which hurts the reading experience. This presents a serious problem because nowadays people are using more mobile devices than desktops for accessing information online. There are many efforts for cross-devices web design, yet they do not work for SVG-based visualization. For instance, if you run this page with Google Mobile Friendly Testing Tool, the results will return that this page is mobile friendly, while in their documentation it says that it's an error to have content wider than screen. However, our visualization community does not have many solutions to this real-world practical and challenging problem as well. There is only one recent work in 2020 that studies techniques for responsive visualization design. They propose a tool to help designers preview and edit visualization on different screen sizes, which, however, still requires significant human intervention and efforts. How about automatic responsive design? One straightforward method is to use decision rules. Consider this example. Let us have 3 rules for the text labels. First, we wrap the lines we can do without breaking words, or use ellipse otherwise. Third, we simply remove text which overlaps with each other. Unfortunately, such rules result into suboptimal solution in real-world case. The axis labels are missing, while the legends become unreadable. This should not be simply considered as an engineering failure. Instead, it reflects the fundamental limitation of rule-based methods. First, the rules are deterministic and could converge to suboptimal results. For instance, a better and flexible solution might be that we put the legend beneath the chart. Second, it's difficult to write rules for real-world conditions because there are too many possible and exceptional cases. This motivates us to ask, can we combine rule-based methods and machine learning models for automatic responsive visualization design? Because rules are mostly interpretable while models can remove the manual efforts of drafting rules. We present MobileVisFixer, a reinforcement learning framework that automatically learns and applies decision rules. Taking an SVG as input, it first decodes it into declarative formats with parameters. The decoder currently supports single-view Cartesian visualizations, and the details can be found in our paper. More importantly, we propose a reinforcement learning method that modifies the parameters to generate mobile-friendly design. Here is a reinforcement learning framework. It includes the environment, which is a chart. Second, an interpreter will observe the environment, return the states and the rewards. We define the state as the mobile-friendly issues and the reward as the changes of the loss function. For example, the current state could be that it has small font size, and the loss function here is simply the font size, let's say 8. Then the machine would take an action to modify the chart based on the policy, which specifies the probability of taking an action A under a state S. For example, the machine might take the action increase the font size by 1. Now the loss function returns 9, therefore it gets an reward as 1. Here is a core message. When an action gets a reward, we want the algorithm to increase the probability of taking this action. For example, increasing the font size when in the state small font size. MobileVisFixer is more complex. It has 29 states which are defined on the type of the mobile-friendly issue and the element type. For instance, X is font size. This makes the model generalizable across different visualizations with different elements. It includes 23 actions for modifying chart parameters such as the axis range and offset values, which can be compatible with third-party algorithms for optimizing the chart layout. We propose a level greedy heuristic to solve the multi-objective optimization problem, which reduces the time complexity and allows the algorithm execute in browser rendering time. Finally, we can interpret the learned policies as probabilistic decision rules, which makes the model easier to understand. For more details, please refer to our paper. This explainability helps us reason about unexpected machine behavior. For example, we found this chart compressed after optimization. By playing back the optimization process, we found that the machine will increase the mean value of the Y range when the axis exceeds the right of the view box. This action reduces the cost, which makes the machine learn to take such actions again. We then realize that this error roots in our definition of our cost function, which is the area exceeding the view box. Compressing the height will also reduce this cost while not solving the out-of-view box problem. Therefore, the correct cost function should be the relative area. There are more examples in our paper where we discuss how this explainability helps us improve our model. To evaluate our method, we conduct the experiment on 21 real-world visualizations. We compare the average normalized return and the successful rates of the initial and learned model. The results show that both models can optimize the visualizations, while the learned model leads to faster convergence rates with less variance, showing that it actually learns good policies to solve the problem. To further investigate the generability of our model, we conduct another experiment on 21 visualizations with a trained model. The results show that MobileVisFixer works for 89% of the visualization. As a take-home message, we would like to discuss automatic visualization design, where there is an ongoing discussion of machine learning models and rule-based methods. While machine learning models are promising, they do not necessarily outperform human-crafted rules, which, however, could be expensive to create. Our work therefore presents a different perspective that automatically learns those rules by using machine learning models. We also support playing back the optimization process to make the automation transparent. With this explainability, we can understand how the model works, interpret and debug unexpected machine behavior. We are excited to extend MobileVisFixer in the future. First, we would like to improve our decoder to support bespoke visualization other than the current conditional charts. We also plan to develop a human-in-the-loop approach that could also learn from human actions. Finally, as the current mobile-friendly test tools do not support SVG-based visualization, we would like to study metrics for mobile friendliness to better reflect the overall quality. With this, I would like to end my presentation and thank you for listening to my talk.
Thank you, Aoyu, for the presentation. We have several questions on Discord again. And the first question I'll select is from Vidya Settler. The question is, how does bot design and interaction retargeting for most by screen work in this system?
And so currently we only consider design because we figured out it's not easy to decode the interactions behind the chart. But actually, I think that's an important problem because in our initial survey of web visualizations, we also found that the interaction remains a very big challenging when we have smaller screens. For example, people might find it difficult to click on a node on a small screen. And to do that, I think we need a computational model to model the interactions. And also we need another method, automatic method to parse or decode the interactions from an existing chart.
Sounds like a lot of interesting future work for our committee to do. Another question from Grit Wongsuphasawat. And the question is, mobile has different screen sizes and orientation. I assume each screen setting will require one run to address the issue. How long does it run take? And is the system fast enough to update on page load, or does it need to be pre-computed?
And yeah, so actually that's a major challenge in our work. So that's why we propose a greedy framework, which tries to solve that in the linear time. So typically it will run in like 3 or 4 seconds, which roughly fall into the page rendering time. But I think the pre-computing the layout will also be a very good alternative, because I think that's exactly what people call adaptive visualization. So we can do some pre-computing and find the good layout on different sizes. Yeah.
Thank you. There are many more questions on Discord, so I encourage people to continue discussing there or try to grab the author in the hallway. Thank you. The next presentation will be about Palettailor, discriminable colorization for categorical data. And the presenters are Kesheng Liu from Shandong University and Mi Feng from Twitter.
Everyone, my name is Kesheng Liu from Shandong University. I'm presenting with Mi Feng from Twitter. Our talk is titled Palettailor, discriminable colorization for categorical data. This is our agenda. Categorical data are everywhere and represented by different kinds of realizations. In many cases, colors are used to include their corresponding classes. A major challenge is that the palette or the assignment to classes might not allow users to visually discriminate different classes in the given data, which makes discriminable colorization a very important topic. Given a multi-class scatter plot, the colorization consists of 2 steps. First, selecting a good palette using existing tools. And second, assigning the palette colors to the classes. However, a random assignment might put similar colors together. Using discriminable color assignment can solve this problem, but it is based on a given palette. So a method that involves color creation to automatically generate a discriminable colorization for given data is necessary. To achieve this goal, we proposed a fully automated approach for creating and assigning color palettes to different visualizations with high discrimination quality. We implemented our measure for a demo system that is presented on an interactive website. Now I'll briefly introduce some related works. The coloring of visualizations contains two steps, palette generation and color assignment. We use three state-of-the-art methods, Tableau 10, Categorical, and Colorization from Qian et al. For this coloring process. For the Tableau approach, palette generation and assignment have to be done manually. For Categorical, the first step, palette generation, is automatic, yet the color assignment step is manual. Colorization is fully automated, but the inaccurate class distance measure and limited color space often result in undiscriminable visualizations. Here comes our approach. Let me first formulate our problem. Given a dataset X or M classes with a background color say 0, our goal is to find a color palette which maximizes the class discriminability with respect to a carefully designed scoring function. We design our method based on both data space and color space. Data space contains a geometry-based class separation measure, while the color space is based on the CIE color difference and color name distance. We use them to quantitatively incorporate point distinctness, color discrimination, and name difference into our objective function. Given the input dataset and background color, to find the best palette in the infinite color space, we use a customized simulated annealing algorithm to rapidly generate a good result. Now let me introduce these three factors. Point distinctness is based on color distinctness and spatial distinctness. It measures the separation between neighboring points from different classes. We use this format to model class separability. However, in the original definition, Wang et al. Used the Qian graph to find the nearest neighbor. This might result in the problem that the neighborhood omega of each point xi does not include all neighbors, thus it may lose local information. To overcome this issue, we propose to use RF-shape as a substitution for the Qian, where RF-shape constructs the neighborhood that includes all neighbors nearby. Color discrimination aims to measure the minimum color difference between each pair of colors from the given palette. Without this term, classes with small overlap might be assigned improper colors. For example, say the green and lime green classes that are hard to distinguish. In addition, we take background color into account by comparing it with each color of the given palette. Without this term, some colors might be hard to distinguish from the background. With this measure, the results with different backgrounds are all discriminable enough. Name difference is used to measure the similarity between colors based on naming patterns. For example, the two colors named blue have a small name difference, while they have a high discriminability. Different color names lead to a large score, such as red and blue. We formulate the name difference as the mean score between all pairs of colors of a given palette. Due to this color name distance, we can create palettes with different color names that help users to describe realizations easily. In order to accelerate the optimization process, we use a customized simulated annealing algorithm. We first generate a randomly initialized palette, as shown on the right. Then we disturb the palette to find a new solution. Simulated annealing will accept bad results according to the temperature-dependent probabilities. We record the best result during the process, and this way get to a satisfied result. We extended our method to different chart types, such as line charts and bar charts. Given the input data, we first discretize it, Thus, they can be treated as special scatter plots. Then we colorize these data points in the same way as shown before. Next, me will present the following sections.
Now let's go to the evaluation part. We wanted to know how effective our approach is at producing discriminable and aesthetically pleasing palettes. So we conducted a user study on Amazon Mechanical Turk that involves 155 participants. We tested out Palettailor on 2 visualization types, 4 types of tasks, and compared it with the 3 state-of-the-art palette generation methods. The study includes 2 experiments, scatterplot and line chart, and here we start with the first one. The experiment had 3 tasks, 2 discrimination tasks and 1 performance task. The first task is counting class numbers. We asked the participants to answer how many classes were presented in a given scatterplot and let them to choose the answer from several options. The second task is comparing class centers. Here we ask the users to judge which of the 2 specified classes had a higher center. The third one was user preference. The participant was asked to choose the plot they preferred from 2 identical plots with different palette check conditions. And we compared Palettailor with 3 state-of-the-art methods with different levels of automation, and our approach is fully automated. In our experiment, to fairly compare Palettailor with existing manual approaches, for example Tableau, we set 2 benchmark conditions representing the systematically simulated best and random cases resulting from the manual coloring process. Similarly, for Categorical, there are 2 conditions. And for the fully automated methods, each has 1 condition. That results 6 conditions in total. And we had 5 hypotheses. For the discrimination tasks, first, Palettailor's results would not be worse than the best case conditions resulting from the simulated manual process, and would be better than random case conditions as well as the fully automated condition. And for the preference task, Palettailor's results would not be worse than the designer-crafted palettes, and would be better than auto-generated palettes. We used the 30 different generated datasets and careful between subjects design for the study. In this table, each row means a different dataset or different kinds of scatter plots. Each column means a different condition. Each cell means a specific group that a participant is assigned to. Each participant performed only 1 task and assigned to 1 group. This covers all the conditions and datasets and minimizes the learning effect. We recruited 105 participants from AMT for the experiment. Each participant went through 3 phases: consent and instructions, training, and then main task. The study results show that, in terms of discrimination tasks, Palettailor is not worse than the best case conditions resulting from the simulated manual process, and it is sometimes better than the random case conditions. And Palettailor is consistently better than the fully automated conditions. For preference task, this chart shows how Palettailor performs against benchmark conditions. A value greater than 0 means that Palettailor is preferred over the other solution and vice versa. We found that Palettailor is preferred over the conditions of the manual crafted palette, and yet is not always preferred over the conditions of the auto-generated palettes. In the second experiment, line chart, we applied a similar experiment design. There are a discrimination task and a preference task, and here we briefly show the results. In general, Palettailor's results in terms of discrimination are not worse than the palettes generated from the manual process. and are consistently preferred over the results of the manual crafted palettes. Recall the high-level question that we had for the evaluation. From the user study, we found that Palettailor, as a fully automated approach, generates color palettes that are comparable with the state-of-the-art approaches in both discriminability and preference. And it consistently generates palettes with a higher discrimination quality than existing fully automated approach.
We also developed a system to assist users, and now it's available online. In conclusion, we proposed the data-aware approach based on simulated annealing for automatically generating color palettes with different visualization types. Then, we quantitatively evaluate the resulting color palettes and visualizations from an online user study. We further developed a demo system for interactive palette generation that is freely available on the web. More details can be found in our website. The system and data are available to use. Thank you for listening.
Thank you, the speakers, for the talk. We have a lot of exciting discussion on Discord, both for this paper and earlier papers. But for this paper, I think the top question is from Ariane. And the question is, does your approach consider color safe for people with visual problems? And to expand on that, for example, people who have color blindness?
Yeah, now we consider this for blinder people, colorblinder people, but in the paper we didn't mention it.
Thank you. And then another question from Dominic. It's related to evaluation. The question is, does preference matters? Wouldn't performance on some tasks be more related?
Yeah, so our goal for evaluation is mainly to test the effectiveness of a Palettailor on users of both discrimination, performance, and the user preference. So in order to evaluate that two aspects, we test users' responses based on both aspects in order to comprehensively evaluate the results.
Thank you. And there are many other questions on Discord. So again, please continue discussing. Thank you for the answers. The next presentation will be about Gemini, a grammar and recommender system for animated transition and statistical graphics. And the presenter is Young-Hoon Kim from the University of Washington.
I'm Young-Hoon. I present Gemini, a grammar and recommender system for animated transitions in statistical graphics. When analyze and communicate data, people create multiple charts and relate them through the transitions. To facilitate these transitions, animation techniques have been studied. About 30 years ago, transitions of a 3D visualization country is animated to help viewers keep oriented. And nowadays, articles animate charts to engage audiences and deliver their stories. Though, creating such animated transition is challenging because current tools are limited. Some tools are limited in terms of expressiveness. For example, Data Clip uses a predefined animation templates so that it cannot express once out of the templates. ggAnimate extends ggplot2 charts by appending few lines of codes, which means it only can animate the transitions within the defined ggplot2 charts, like data transformations. Other tools requires a significant effort to use. For example, D3 requires users to write JavaScript code for selecting low-level visual components and assigning new values. Kanit, the most recently proposed tool, offers a higher-level grammar, but still users need to select the low-level components like D3 and extend the existing SVG format visualization to DSVG format. On top of that, also have to consider a lot of design choices, such as staging, which separates changes into multiple steps to elaborate the process of the given transitions. The right tool shows the staged and not staged animations. Users also have to consider timing, including pauses, duration, delay, staggering, and temporal distortions. The right three show some variations by timing. The top animation can be staggered like the bottom left, or can take a linear temporal distortion like the bottom right. To allow people to easily explore various animation designs, we contribute Gemini, a grammar and recommender system. With the Gemini grammar, two given charts can be animated by specifying a spec. And by leveraging this grammar, Gemini can recommend multiple staged animation designs for the given transitions. In the rest of this talk, I'll go through the core components of grammar and how the recommendation works, then I will talk about our evaluation. So, the first is the grammar. Two single-view Vega charts can be animated by specifying a spec in the Gemini grammar. Let me briefly demonstrate the Gemini grammar through this example, which zooms out the view and extends the lines like this. Let's see one more time. Zooms out the view and extends the lines. A Gemini animation is composed of steps, which are basic animation units. Step is composed of three properties: component, change, and timing. Component is to select a visual component to control. It uses the type of the component and its name. Here I create steps of x-axis, y-axis, and line mark. Then step specifies changes of the selected component, such as data, scale, encoding. The default is changing all of them from the initial state to the final state. In this example, I'll modify the mark step into two ways. Change all except for its data, and change all except for its scale. As a result, the x-axis step specifies these x-axis changes, and the y-axis step specifies these y-axis changes. The mark step without changing data will only rescale. The mark step without changing the scale will only extend its data. Finally, steps requires a timing to specify timing information such as duration, delay, staggering. Here I'll simply set all duration as 1 second. These defined steps are combined into a timeline by two composition rules, sync and concat. Sync synchronizes the steps, so these three steps can be synced to be played together to show this. Concat concatenates the steps, thus the last step can be concatenated to the synced step to show the later part of this animation. By placing this to timeline property, a Gemini spec is completed. Here's the final animation of the spec. The Gemini grammar supports various animation designs such as staggered mark movements and enumerated changes along with data. Please check out our paper and GitHub repositories to see more examples. By leveraging this grammar, we develop a recommender system. For given transitions and user-provided parameters, such as the number of stages and total duration, Gemini recommends staged animation designs. The recommendation process has 3 steps. First, Gemini detects the changes of visual components between the start and the end state. In this example, X and Y axis change their scales, and line mark change their scales and extend data. Then, Gemini combines these detected changes to enumerate timelines with the user-provided number of stages and total duration. Let's say a user wants a 2-stage animation for 2 seconds. The 5 changes are combined into timeline as shown. Then, Gemini excludes a timeline having illegal intermediate states or data overflows. For example, Gemini excludes the timeline 3 due to the overflow created by inserting new data before scaling the chart. Please see our paper to see more details of exclusion rules. Finally, Gemini ranked the enumerated timelines by its complexity score, which is a proxy for how much human effort will cost to follow the given animation. It assumes that each change has a cost, and stages have a capacities of the cost as a function of duration. In this case, since each stage is 1 second long, the capacities of the stages are 10. We use the sigmoid function as shown so that capacities get converted to the maximum capacity as the duration increases. Also, it assumes the bundling effect, which gives penalty or discount when certain changes happen simultaneously. For example, if this x-axis change and Mark's x-scale change happen together, we discount the cost to promote it, because it maintains a valid visual encoding like this. After applying all bundling effects, Gemini sums all costs of each stage, and the total surplus of the cost becomes the complexity of the timeline. Each score and function parameters were hand-tuned in accordance with GraphScape's edit operation ranking. To check this measure, we conduct a user study. We recruited 53 subjects from Amazon Mechanical Turk. Each subject ranked 5 different Gemini recommendations of a given transition in terms of how well they represent the transitions in a clear and logical way. They repeated the task for 4 transitions covering various transition types. We compared Gemini's ranking with the collected users' ranking. Here, the x-axis indicates the ranking by Gemini, and the y-axis indicates the average user's ranking. It shows that Gemini ranking is not well aligned with the user's preferences. So we tuned the parameters of the complexity function to fit better with the observation. Finally, we evaluated if Gemini can help animation authoring process. To verify that, we conduct a study replicating user-crafted D3 animated transitions by Gemini. We recruited D3 users with data visualization experience and gave them D3 calls of the start and end charts of a transition. Then, we asked to create animated transitions between them by using D3. After collecting the participants' animations, we replicated them by editing the top 3 Gemini recommendations for the given transitions. So the more the user-crafted animations are replicated in the Gemini, the greater expressiveness Gemini has. And the fewer amount of the edit on the recommendations for the replications indicate that the better recommendation quality. As a result, 8 D3 users created 11 animation designs for 4 transitions. 9 out of 11 were successfully replicated in Gemini. The one is not replicable, since its line mark applies different timing on X and Y scales. The other one is partially replicable, since it squeezes the Y-axis and bars. But Gemini cannot squeeze the Y-axis title. On top of that, 8 out of 11 animations can be achieved with minor edits to the Gemini recommendation, such as changing timing and inserting a new step. Also, users spend 40 to 150 minutes to animate the given transitions, and made mistakes in 7 animations, such as missing and unexpected changes. While Gemini took less than a minute to recommend the animations without mistakes. In conclusion, Gemini provides reasonable expressiveness and reliable recommendations as starting points. In other words, by employing Gemini, animation authoring tools could provide recommendations to facilitate the authoring process with initial designs. Thank you for paying attention for this talk. If you want to know more, please use the right QR code, which included extra examples that I didn't cover this talk, and the details of the evaluation result, and etc. Thank you.
Thanks, Yang-Hun, for the talk. And before I ask question, I would like to point out that if you see Yang-Hun's background, he is actually on the job market soon because he's wrapping up PhD in this academic year. So if you're looking for talent, then reach out to him.
Yeah.
For question, that's a question from Wolfgang that in the basic example that you walked through, how are the axis changes defined in terms of target values?
Yeah, thanks for question, Wolfgang. Actually, Gemini find the differences by investigating the start visualization and visualization. So in that example, actually there's the visualization spec changes in between the two things, but the internal calculation of label positions or labels are are changes in there. And Gemini doesn't require to specify the changes because the default of the step component is changed all from the initial state to the final state, so that there's no description of the change in that example.
I see. And then another question that I have is, I'm curious to hear if, in general, does Gemini produce a big variety of recommendation, or are there usually just a few ways to do transition for certain, start and end that you specify?
Yeah. Could you say one more time?
Oh, so for the set of recommendation that Gemini produced, are there like big variety, or are there usually just a few ways that's like the best?
There's a lot of thanks for the question. There's a lot of variations, but it is hard. But most of them are useless in my opinion. So that so users can control the number of the recommendation by giving up parameters such as the number of stages and some parameters about the information about transition, whether the axis changes the scale or not. So there are a lot. So there might be so that the evaluation of each enumerated animations was critical to get a useful one.
Thank you. Seems like I have a few more questions, but we can follow on Discord. Okay, so the last paper, last but not least, is Risk Commander, Computing Text-Based Similarity in Visualization Repositories for Content-Based Recommendation. And the presenter is Michael Opperman from the University of British Columbia.
I will present Risk Commander. This is joint work together with Robert Kincaid and Tamara Mansner, a collaboration between UBC and Tableau. Organizations and communities accumulate masses of visual data representations over time, and large-scale visualization repositories emerge, which leads to major challenges. Users have difficulty in discovering relevant content,
and users often start from scratch instead of reusing existing content. Recommendation systems are increasingly used to assist users by surfacing relevant content. The VIS community typically uses the term recommendation in the context of recommending new visual encodings for a given dataset or a combination of data types. Examples are Tableau Show-Me, Voyager, Draco, or Data to VIS. Recently, there was a lot of progress in this area, but automatically generated results are still relatively simplistic. Our goal is not to recommend visual encodings. Instead, we follow the more traditional terminology of the recommender systems literature, where recommendations are proposed for pre-existing items of content. We want to surface existing visualization workbooks that can be very complex, that have been created by users, and are stored in visualization repositories, such as Tableau Server. We can differentiate between two major recommendation paradigms: content-based filtering and collaborative filtering. Content-based filtering is the focus of our work. We want to find relevant items based on the actual content. These recommendations are usually less diverse, but more accurate. This approach allows also the identification of near duplicate items, which are highly relevant in some cases, but need to be excluded in other cases. And then there is collaborative filtering, which doesn't look at the content itself or features of an item. Instead, it analyzes the interactions between users and items and derives recommendations from usage patterns. It's a popular approach because it requires no domain knowledge, allows fast computation, and leads to serendipitous recommendations. But a major disadvantage is the cold start problem for new items or users, besides being disconnected from the content. The advantages of both collaborative filtering and content-based filtering can be combined into a hybrid system. But that's future work and not the immediate goal of this project. Our process is driven by two key questions: which content features are most informative for comparisons, and what techniques can be used for comparing and ranking VIS specifications. As a result, we propose a text-based similarity measure for content-based recommendations to facilitate information seeking in visualization repositories. We worked closely with the recommender systems group at Tableau and interviewed machine learning engineers, a UX designer, and a product manager frequently. This collaboration allowed us to get insights into typical use cases and pain points related to working with large VIS repositories. In parallel, we extracted and analyzed features from VIS specifications and developed different generations of prototypes. To better understand the appropriateness of various content-based models, we conducted a crowdsourced user study where we compared human judgments with model predictions. I will explain it in a few minutes in detail, but these results of the study informed our proof-of-concept recommendation model, and we demonstrate its utility in our VIS commander prototype. But let's take a step back and look at the underlying data. We focus on Tableau workbooks that often contain multiple sheets and dashboards, roughly comparable to a spreadsheet. All components are described in the XML specification. We extract text content such as titles, captions, and access labels. And we also use the data source column names as additional text data, such as city, customer name, and sales, that are also part of the XML VIS specification. Originally, we considered using a combination of extracted text features and visual encoding features. We implemented it in a first prototype where we could define weights for the underlying topic versus the visual style. But visual similarity is tricky. Some workbooks are perceived similar, although they use different data and about completely different topics, as you can see here. In contrast, identical information may be visualized fundamentally different. For example, CO2 emissions in different regions as a bar chart or pie chart. We ultimately decided to leave out visual encodings. If the task is design inspiration or learning, the visual style is absolutely necessary. But we identified information seeking as the core task when browsing VIS repositories in enterprise settings, where the goal is to find informative workbooks around the user-specific analytical questions. So we choose to focus on the subject matter of a workbook and not the visual style, such as marks, colors, or layout properties.
We argue that the visual style can add noise to the model when the task is purely information seeking. We identified multiple challenges related to extracted text data from VIS specifications. Most important, text in VIS workbooks is very different to normal text documents with sentence structures such as news articles. Often we have only single words or short phrases, so we try to use as much content as possible. A workbook often contains multiple dashboards or sheets, but we decided to only recommend whole workbooks and create a single bag of words. So we consider a workbook as the object of interest. We found many incomplete workbooks, so we use basic filtering techniques to exclude some of those. More work is necessary to better understand what low quality actually means and to implement appropriate filter options. We also found many duplicates or near identical workbooks. A content-based model should be able to identify those. Workbooks have a domain-specific nature and often use company internal vocabulary, which influences the choice of NLP models and the use of pre-trained models. So we start with a bag of words from a workbook, but how do we transform it into a vector? And how do we make comparisons in order to create meaningful VIS recommendations? To answer these questions, we conducted a review of models and selected a subset of 4 natural language processing models and distance measures. TF-IDF as a baseline, LSI, LDA, and word embeddings, specifically dog to vec and glove. In addition to an informal analysis of NLP models, we conducted a crowdsourced study to collect human similarity judgments and compared it with the algorithmic notion of similarity. Of course, many other approaches have been proposed to evaluate recommendation algorithms, such as A/B testing. But our goal was to analyze just the similarity measure as a first step, a comparative model analysis independent of the user interface. So how did we collect these similarity judgments? We sampled triplets of VIS specifications with 1 reference VIS and 2 alternatives each. And we asked 75 participants to pick the alternative that is most similar to the reference. Then we ran the same task with different NLP models and we compared the agreement. The study interface showed the extracted text and not the visual encoding. Participants were asked to select the most similar alternative based on the overall topic. Each participant rated 47 of these triplets, and we manually verified that the text is understandable and doesn't use extensive domain-specific terms. After the study, we computed agreement scores. Most relevant is the agreement between the participants and the models. On a scale from 0 to 1, the agreement is very high for all models. We observe a very good alignment between human judgments and off-the-shelf model predictions. All models achieved high agreement scores. LDA performed slightly better in our experiment. This is only a subset of popular NLP models, but our results show that more complex models don't necessarily lead to major benefits compared to simpler models. We don't have long English text documents that are rich in information, but our study demonstrates that meaningful pairwise comparisons are possible, which are the foundation for content-based recommendations, despite very limited text, no grammar, no real sentence structure. So we chose to implement an LDA-based model in VIS Commander. We can select an example workbook and open its detailed view. This view shows an interactive version of the workbook. At the bottom of the screen is the recommendation panel, divided into different similarity facets. Our requirement analysis revealed that a single category of recommendations is not sufficient to capture all the tasks that should be facilitated. Therefore, we divided recommendations into 3 different facets. The goal of the related workbook facet is to show semantically related workbooks but not near duplicates. For the similar data source facet, we train a separate model with only data source column names. Very often we see multiple versions of workbooks, for example at 2019 and 2020 report, or as you can see here, different crime dashboards. We bundle them in the similar versions facet. In this project, we have focused on Tableau workbook specifications. But most visualization systems such as Power BI, Qlik, or Looker have similar textual features for describing visualizations. The feature extraction depends on a specification format, but the basic process we outline in our paper and the findings of the user study should be applicable to any repository of machine-readable VIS specifications. Please have a look at our paper for a detailed discussion of challenges related to content-based VIS recommendations. We contribute the design and implementation of a proof-of-concept recommendation pipeline consisting of feature extraction, pairwise comparisons, and the user interface. We analyzed different NLP techniques and conducted a user study to assess the alignment between model predictions and human judgments of similarity. And with that, I'm happy to take questions.
Hello. Thank you, Michael, for the presentation. We have a question from Wolfgang that, do I understand correctly that similarity search is based on example notebook only? Can I also define what I'm looking for?
Yes, in this first version, we focus on a single example. So you click on one workbook, or you open the interactive version, the detailed view of one workbook, and then you get recommendations. This approach could be extended to a sequence-based model where you kind of look at the last few examples.
I see. And then a question from Alper is that how do you see this pipeline enriching the data culture experience of BI users?
Not exactly sure what data culture means in this context, but yeah, we did some user studies at Tableau and found out that it improves the workflow to find workbooks that are relevant for their analysis task. So instead of typing something in the search field, after looking at the 2019 report, they can quickly open the recommendation panel and open the 2020 report, for example.
So our project expand the meaning of data culture that he say by saying it means being able to understand the well of data that well of data available to them.
Yeah, that's a good point. I think the recommendations really help to make kind of serendipitous discoveries and see maybe workbooks from other teams that would be somewhere hidden in a deep folder structure. And by looking at the semantic content, we can surface them and provide meaningful recommendations.
Thank you. And I think there's now time to conclude the session. We have a lot of exciting discussion on Discord, and we should continue doing that and maybe take some of these to hallways. Thank you.
We propose data-driven space filling curves. Our new method generates linearizations that better preserve coherency than existing techniques.
Our method supports 3D datasets, and even multi-scale data on a quad tree or an octree. Many visualizations benefit from our method, for example, visualization of multivariate particles, and visualization
Language models are highly performant across many language understanding tasks. Comprehending the linguistic knowledge encoded by these models, however, remains a challenging problem. We introduced an approach for visually analyzing contextualized embeddings produced by language models. Our design shows how much context is captured by embeddings, the ability of embeddings to capture meaningful text spans, and linguistic relationships represented by the embeddings.
Different sampling strategies have different performances in preserving features, but which one is the best? In this paper, we selected 7 sampling strategies along with 8 representative datasets and 3 important visual factors. We formulated 4 hypotheses and conducted a user study with 100 participants. For the derived insights, please refer to our paper.
There are many similarities between visual analytics and interactive optimization. The design of visual interfaces for optimization systems is an application of visual analytics. However, many optimization systems are automated. If you are thinking of building an interactive optimization system, come to our talk. We have prepared some tips for you.
Data stakeholders are rarely the data experts. Making tools for them means considering how they communicate about data. Rules are a convenient way for humans to express patterns in data, like we need high variable x and low variable y. In our human-in-the-loop approach, the user selects points of interest and can immediately see rules that differentiate those data from the rest. Lots more detail in the paper, even though it's short.
Hey everyone, I'm Jian-Guang, a PhD candidate at Purdue University, computer graphics major, and a research internship at Bosch Research North America. Here, we are presenting our recent research, Process Viewer, using factorized prototypes to visually interpret and diagnose deep neural network. This work is co-authored by research scientists at Bosch, Zhang Dai, Dr. Panpan Xu, and Dr. Liu Ren.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Blockchain has gained more attention and its applications are emerging. We collect 76 blockchain visualization tools and systematically classify them into 5 aspects: target blockchain, blockchain data, target audience, task domain, and visualization type. In the end, we look at open challenge in blockchain visualization.
Firstly, we extract contours of virions and distribution of spike proteins. From a newly estimated contour, a 3D mesh with evaluated triangles is obtained. In the last step, rules describing relations between protein instances are defined by the user. The resulting model is created by application of all rules on the generated 3D mesh.
Nowadays, data is often distributed and owned by different participants. There is an emerging need to provide a joint visualization, such as a TS&E projection, to serve as the full picture in data analysis. If the participants are privacy sensitive, how can we build a joint projection without data leakage? Conventional embedding algorithms, such as the TS&E, are designed for single-site computation and require data centralization. Privacy leakage may happen in 3 stages in the visualization pipeline.
Many techniques can be used to render and visually explore large 3D line sets